This lecture is on Bernoulli's principle and pressurized pipe flow. Let's start with the principle of continuity. The principle of conservation of mass states that matter cannot be created or destroyed, and it can only be changed into a different form of matter. The conservation of mass principle can be applied to fixed volumes, known as control volumes. In this volume, mass entering per unit time equals mass leaving per unit time plus increase of mass in the control volume per unit time. For a steady flow, in which where the fluid's velocity and direction at any given point do not change over time, we have no increase in the mass within the control volume. As a result, mass entering per unit time equals mass leaving per unit time. And mass entering and mass leaving per unit time can be shown using m dot. So for the mass entering per unit time, we can use m dot in, and for mass leaving per unit time, we can use m dot out. And m dot basically is the mass flow rate. M dot is mass flow rate, and that equals rho times delta A times V, and the units are mass per time. So in the format of a formula, we can write this sentence as rho 1 delta A1 V1 equals rho 2 delta A2 V2, which equals a constant, and that equals m dot. So this is the equation of continuity. For incompressible fluids, the density does not change, so rho 1 equals rho 2. So basically, rho cancels in this equation, and what we get is A1 V1 equals A2 V2, and that equals Q. Here, A is the cross-sectional area, for example, of a pipe. V is the velocity of the fluid, and Q is the flow rate. So Q equals AV, and based on the continuity principle, A1 V1 equals A2 V2. As an example, this pipe has different cross sections. Like at this point, the cross section is larger than here, but the Q is the same. Flow rate in this pipe stays constant. So as a result, discharge at section 1 equals discharge at section 2, or Q1 equals Q2 because flow rate is not changing. As a result, we can write A1 V1 equals A2 V2. So if we know that A1 is, for example, 10 times 10 to the negative 3 meters squared, and A2 is 3 times 10 to the negative 3 meters squared, and if we know V1 at this section, we can calculate V2 at this section using this formula, which is the continuity formula. So using these three known values, we can find V2, velocity at this point, which is A1 V1 divided by A2. So that equals 7 meters per second. So at this section, where the cross section was larger, the velocity was 2.1. And as a result of this contraction, the velocity increases to 7 meters per second. And we found that based on the continuity equation. Another example is determining the velocities in pipes coming from a junction. So here, total mass flow into the junction equals total mass flow out of the junction. So basically, we can write Q1 equals Q2 plus Q3, or A1 V1 equals A2 V2 plus A3 V3. According to the principle of conservation of energy, when friction is negligible, we can say that sigma or the sum of kinetic energy, which is basically 1/2 times mv squared, plus sigma of gravitational potential energy, which is mgh, is constant. So here in this formula, m is mass, v is velocity, and h is height above the datum. And to apply this to a falling droplet, the initial velocity of the droplet is 0. Therefore, the initial kinetic energy of the droplet is 0. Initial height of the droplet is h. Therefore, the initial potential energy of the droplet is mgh. The final kinetic energy when the droplet touches the ground is 1/2 times mv squared, and the final potential energy is 0. So we can write initial kinetic energy plus initial potential energy equals final kinetic energy plus final potential energy, or 0 plus mgh equals 1/2 mv squared plus 0. A similar method can be applied to a continuous jet of liquid. So here, the sum of the kinetic and potential energies remains constant. So mgz1 plus 1/2 times mv1 squared for this point equals mgz2 plus 1/2 mv2 squared, which is for this point. Since m is constant, it cancels. So this formula simplifies to 1/2 times v1 squared plus gz1 equals 1/2 times v2 squared plus gz2. But in the situation where we have a pipe and there is flow inside the pipe, the pressure is also different from point to point. So if the pressure is different, such as this case, this angled pipe in which it has a fluid of density rho inside, there would be an extra force acting due to this pressure difference. Therefore, net force due to this pressure difference does work on the fluid. So if you remember, work is force times distance, and force is pressure times area. So work becomes P dot A dot D. P is pressure, A is area, and D is the distance. A times distance is the volume, so work becomes P dot delta V. We know that work is energy and has units of Newton times meter, which is joules. So based on this formula, we can say that pressure is basically energy per unit volume. So between point 1 and 2, we can write P2 minus P1 equals gamma H, or rho G times Z1 minus Z2. Or if we rearrange it, we get P1 over rho plus GZ1 equals P2 over rho plus GZ2. And adding the impact of pressure difference to the equation derived for constant pressure, we get the Bernoulli's equation, which is P1 over gamma plus V1 squared over 2G plus Z1 equals P2 over gamma plus V2 squared over 2G plus Z2, which is constant. So Bernoulli's principle describes the relationship between fluid velocity, pressure, and elevation. Therefore, since left and right side of this equation should stay constant, faster moving fluids exert lower pressure. So if on this side of the equation, V increases, in order to balance the other side, P should go down. So higher velocity corresponds to lower pressure to keep this equation constant. So faster moving fluids exert lower pressure. So this is a sample application of the Bernoulli's principle. A plane wing. A plane wing is designed with a curved upper surface and a flatter lower surface. So due to the conservation of mass, air above the wing, which is this red line, is forced to move faster due to the curve, and air below the wing, which is this blue line, moves slower because it follows a shorter, flatter path. As a result, faster air above creates lower pressure, and a slower air below creates higher pressure. As a result, there will be a lift. Because pressure is low here, pressure is high here, so the resultant force would be upward, that is the lift. Let's watch a video. So what is happening here, as you can see, the cross-sectional area here is smaller than here and here and here. So as the air is blown from left to right, the velocity of the air increases here, and based on Bernoulli's principle, as velocity increases, pressure decreases. So as pressure decreases here, the pressure inside this pipe will be less than the atmospheric pressure. So the atmosphere pushes up this fluid through this pipe here. And same happens to this one. And as blowing air stops, the fluids return to their initial position. Example. Consider the flow of air around a bicyclist moving through still air with velocity v1. Determine the difference in the pressure between points 1 and 2. So if we write the Bernoulli's equation between points 1 and 2, since points 1 and 2 have the same height, z1 and z2 cancel out, the question tells us that v2, the point that air touches the face of the bicyclist, v2 is 0, so this term also becomes 0. Since v2 equals 0 and z1 equals z2, this whole equation simplifies to p1 over gamma plus v1 squared over 2g equals p2 over gamma. If you rearrange that, delta p, or p2 minus p1, becomes 1/2 times rho v1 squared. Another example. A large open water tank has a small outlet near the base. The water level in the tank is 5 meters above the outlet. Assuming the velocity of the water at the top of the tank is negligible, use Bernoulli's equation to determine the velocity at which water exits the outlet. Okay, so we write the Bernoulli's equation between point 1 and 2. Since both 1 and 2 are open to the atmosphere, we have atmospheric pressure, so these two fractions cancel out. V1 is 0 because the question says the velocity of the water at the top of the tank is negligible. So this term, or basically this fraction, also becomes 0. Z2 is also 0 because it's at the very bottom of the tank. So what we get is only this fraction and this number here. So if we solve it for V2, we get V2 equals 9.9 meters per second. Another example, a stream of water of diameter d equals 0.1 meter, which is for this point, flows steadily from a tank of diameter d equals 1 meter. Determine the flow rate Q needed from the inflow pipe if the water depth remains constant. H equals 2 meters. So from the Bernoulli's equation between points 1 and 2, we have P1 over gamma plus V1 squared over 2G plus Z1 equals P2 over gamma plus V2 squared over 2G plus Z2. So assuming that P1 equals P2, because both are open to the atmosphere, and Z1 minus Z2 equals H, we get V2 squared minus V1 squared equals 2GH. So as you can see, this equation has two unknowns. So another equation is needed to solve this one. Here using the continuity equation, Q1 equals Q2. So A1V1 equals A2V2, in which A1 is pi d squared over 4, which is for this point, and A2, which is for here, is pi times d squared over 4. So we can write V1 equals small d over capital D squared times V2. So substituting into the Bernoulli's equation, we get V2 squared minus, instead of V1, we put this value inside the parentheses, squared equals 2GH. So solving for V2, we get V2 equals 6.26 meters per second. Since we found V2, which is the exit velocity of the flow from here, Q equals A2V2, which is pi times 0.1 meters squared over 4 times 6.26 meters per second. So the flow rate will be 0.049 meter cubed per second. Next topic is on flow regimes in pressurized pipe flow. So the dimensionless parameter Re, which is the Reynolds number, is used to identify the flow regimes. The Reynolds number, which is Re, equals rho v d sub h over mu, that equals v times d sub h divided by nu. So here rho is the density of the fluid, v is mean velocity of the fluid, d sub h is the hydraulic diameter, which equals 4 times a divided by p, in which a is the flow area and p is the wetted perimeter of the cross-section, that is the portion of the pipe or channel boundary that is in direct contact with the fluid. Mu is the dynamic viscosity of the fluid, and nu is the kinematic viscosity, which equals mu divided by rho. For pressurized pipe flow, if the Reynolds number is less than 2000, it is laminar flow. If the Reynolds number is between 2000 and 4000, it is transition flow. And if Reynolds number is greater than 4000, it is turbulent flow. Let's look at some common hydraulic diameters. So if the geometry is a circular tube or pipe, d sub h is 4 times a divided by p, in which here we have 4 times pi d squared over 4 divided by the wetted perimeter, which is pi times d. So if we simplify this fraction, we get d. So the hydraulic diameter for a circular tube or pipe, which is completely filled with water or fluid, is basically d. For a square duct, d sub h is 4 times a squared divided by 4a, which becomes a. For a rectangular duct, which is fully filled, d sub h equals 4 times ab divided by 2 times A plus B, and that equals 2AB divided by A plus B. And for a channel of water or partially filled rectangular duct, D sub H, which is a hydraulic diameter, equals 4AB divided by 2 times A plus B. So 2 times A plus B is basically the wetted perimeter. Example: the flow rate of chocolate syrup is 4 meters cubed per second, and the cylindrical pipe in which the fluid flows has a diameter of 6 centimeters. Determine the Reynolds number for the fluid which has a density of 1,268 kilograms per meter cubed and a viscosity of 17 pascal second. In addition, indicate if the flow regime is laminar or turbulent. So let's list the known values. We know that Q, which is the flow rate, is 4 meters cubed per second. D, which is the diameter, is 0.06 meters. Rho, that is the density, is 1,268 kilograms per meter cubed, and viscosity, which is mu, is 17 pascal second. First, let's find the velocity. Based on the formula Q equals AV, V becomes Q divided by A. So we get V equals 1,415.4 meters per second. So plugging in the numbers in the Reynolds number, we know rho, we know V from here, we know D, and we know mu. So the Reynolds number becomes 63,384.7, which is greater than 4,000. Therefore, the flow is turbulent. Energy loss in pipes. Energy loss in pipes can be categorized as the following. We can have major energy loss, which is due to friction, and minor energy losses due to sudden expansion, sudden contraction, bend in pipe, pipe fitting, or an obstruction in the pipe. To account for major energy losses in the Bernoulli's equation, we need to add another term on the right side of the equation, which is HLF. Example: for the simple pipe system shown in the figure, the pressures are P1 equals 14 kilopascal, P2 equals 12.5 kilopascal, and P3 equals 10 kilopascal. Determine the head loss between 1 and 2 and the head loss between 1 and 3. The discharge is 7 liters per second. So we write the energy equation between 1 and 2. Because the diameter of the pipe is not changing from 1 to 2, velocity stays constant. So these two fractions would be the same. And also the height is not changing, so Z1 equals Z2. As a result, this whole formula simplifies to P1 over gamma equals P2 over gamma plus HLF from 1 to 2. And by plugging in the numbers, we get HLF from point 1 to 2 equals 0.15 meters. The energy equation between point 1 and 3. So we write the same thing, but this time from point 1 to point 3. And HLF from point 1 to point 3. Again, we calculate V. So V1 equals Q divided by A1. So we get 2.48 meters per second. V3, Q stays constant, but the diameter of the pipe is changing. So V3 becomes 5.39 meters per second. By plugging in the numbers into this equation, we get HLF from point 1 to 3 equals 4.24 meters. Next, we're going to talk about minor losses. So they are head loss caused by inlets, outlets, bends, expansions, contractions, valves, and fittings. So the more complete form of the energy loss equation is H sub L equals H sub LF, which is due to friction, plus H sub Lm, which are minor losses. And H sub Lm equals sigma KL times V squared over 2G. And here, K sub L is the loss coefficient. So for inlets and exit transitions, we have different KL values. So when fluid enters a pipe from a reservoir, it will cause a minor loss, and it depends on the type of transition. So for example, for a very smooth kind of transition from a reservoir into a pipe, in which R of this radius, or radius of this circle, divided by D, which is the diameter of the pipe here, is greater than 0.15, then K sub L equals 0.04. And then K sub L of this case, which is from a reservoir to a pipe but at 90 degrees, is 0.5. So as you can see, the loss is greater than here. Another case where the pipe extends into the reservoir, where L is greater than D over 2, KL is greater than, it is equal to 1. But for a case that a pipe is connected to a reservoir like this, from left to right, KL is always 1, and at the discharge end of a pipe into a large reservoir, KL is 1 regardless of the shape of the transition. Expansion and contraction. So connections between pipes of different diameters are subjected to minor losses. Here we have some examples of sudden expansion, sudden contraction, gradual expansion, and gradual contraction. So K sub L for a sudden expansion depends on the diameter of the pipes. So it is equal to 1 minus d1 squared over d2 squared, everything to the power of 2. And for example, for sudden contraction, you have to use this graph in order to find the KL value. And we have tables based on the theta that we have here and here, in which you have to use those in order to get the KL value for each of those theta angles for gradual expansion and gradual contraction. Pipe fittings. So bends and valves also cause energy loss in pipes. And this table here shows corresponding KL values for each of those. For example, for a gate valve, which is fully opened, the KL is 0.19. And for a globe valve, fully open, the KL is 10, which is a pretty high number. So let's see what is the procedure of analysis. So problems that involve flow through a single pipeline must satisfy both the continuity equation and the energy equation, and account for all the major and minor head losses throughout the system. So we need these two formulas. This is a continuity equation, and this is the complete form of the Bernoulli's equation that has major loss and also some of minor losses involved in it. Example. Water flows from the basement to the second floor through the 2 centimeter diameter copper pipe at a rate of Q equals 0.8 liters per second and exits through a faucet of diameter 1.3 centimeters as shown in the figure. Determine the pressure at point 1. If A. Viscous effects are neglected, which means that there will be no loss. B. The only losses included are major losses. And C. All losses are included. So first thing that we have to do is listing all the known values like Q, which is equal to 0.8 liters per second, diameter of the pipe, diameter of the faucet, epsilon, which is the roughness of the pipe, rho, which is the density of water, and nu, which is the kinematic viscosity. So V1 equals Q over A1. By plugging in the numbers, we get V1 equals 2.546 meters per second. So the Reynolds number, that is Vd over nu, becomes 4.5 times 10 to the fourth. As a result, the flow is turbulent. So part A of the question, that was energy equation between 1 and 9 with no loss, we will have H1, which is the total head at 1 equals the total head at 9 because there's no loss. So the Bernoulli's equation will have no major or minor head losses. Z1 equals 0 because the datum is here, so it has 0 height. P9 is 0 because it's open to the atmosphere, so pressure is 0 here. V9, velocity at this point, is Q divided by A9, and that's equal to 6.027 meters per second. So by knowing all the numbers that we need, P1 equals 94.6 kilopascals. So this is for case 1 where there was no major or minor loss in this pipe system. P1 equals 94.6 kilopascals. Part B, we have only major head loss. So H1 minus the major head loss equals H9. So what's the difference between P1 here and there? We have to add this formula of FL over D times V squared over 2G for major head loss. We know the epsilon, so we find the epsilon over D. We already know the Reynolds number, so from the Moody diagram, we get F equals 0.0215. Total length of the pipes is 22.6. Therefore, plugging in all the numbers that we found, P1 equals 173.3 kilopascals. So as you can see, it has to be higher because there will be some energy lost in the pipe. So pressure at 1 should be higher than case A, where there was no loss in the pipes. And case C is including major and minor losses. So we add the minor losses here. Sigma Ki is basically adding all these K values, and that equals 17.3. And by knowing all the values that we need for this formula, P1 equals 229.4 kilopascals. So as you can see, this number is the greatest. So by including all the major and minor losses, pressure at 1 should be the highest, which is 229.4 kilopascals.